It's a great pleasure to be here again to give my next lecture in the Gresham series. So today I'm going to discuss a very interesting question, namely, are we the unique place where intelligent life exists in the galaxy or in the universe, or are there others elsewhere on distant planets? And if so, where are they? And so this "where are they" question seems to be first posed by Enrico Fermi, who is known for being, in some sense, the father of the nuclear bomb. He discovered some very important processes that led to our understanding how nuclear energy can be liberated. Anyway, so one day when he was working in Los Alamos, he and his colleagues went out to lunch, and he was this sort of amazing character who could just conjure up ideas out of nowhere. And so he posed the question to his friends around the table, where are they? And he went through little calculations on the napkin at lunch, showing that, well, if there were lots of other species out there on different planets, they would have been around long before we had developed on the Earth, and they should really have shown their presence, and we haven't seen them. And so his conclusion that in the absence of taking flying saucers seriously or whatever, that maybe they really were not there. And so this has led to this was the first recorded idea about this question. I'm sure people have asked it before, but this gave rise to this phrase of "where are they?" If there are any other aliens out there, where are they? Why haven't we seen them? Okay, so the Milky Way has vast numbers of stars, about 100 billion stars. Each of those stars has planets of some sort around it, almost certainly. We've only sampled, a few thousand of the most nearby ones, and many of those do indeed have planets, systems of planets even. And now, not all of those planets are ideal for making life. Some are too hot, some are too cold. But just as in the Goldilocks story, some are probably going to be just right. And I want to try to explain to you today what just right means, and how we're conducting searches, proactive searches, to look for evidence of what might be out there. And so the big question we have is, do they have life on them? And this might just mean vegetation or whatever, but a more fundamental question, much, much harder, is, do they have intelligent life on them? And we have ideas. The answer is we've found nothing yet. No signs of life, no signs of anything yet, but we're looking, and we think that as we expand the numbers of targets we look at, and I'll explain how we do that, we might someday have a chance of finding something. And this search is inspired by people like Konstantin Tsiolkovsky, who was the father of space flight, basically. He invented the first concepts, Russian, and he said, the Earth is the cradle of the mind, but we cannot live forever in a cradle. And it's that theme that I want to develop a little more. Now, the basic reason for believing that life should occur frequently elsewhere in the galaxy is because Charles Darwin gave us the basic understanding of evolution. He talked about some warm little pond when life began on the Earth, with all sorts of ammonia and phosphoric salts and light and heat, and even lightning, electricity, that's what he means. And then somehow you could form proteins out of this organic mush, and that would then take on more complex changes and eventually build its way up into us, basically. But after many false roots and false connections, whatever. And so we believe that there was, the current view is there was some primordial soup, we call it, which began 3 billion years ago, probably, on the Earth, when we first had the beginnings of an oxygen atmosphere. That's when organic life suddenly developed. And it exponentiated, well, here we are. Okay, so the first point I'd like to try to get across is that life is incredibly robust. It can exist in extreme conditions. And so we've found signs of life in the most coldest situations you can imagine, on the tops of the Himalayas on the Earth, in the deep oceans. And we've also found signs of life, primitive cells, or self-reproducing cells, even in near volcanoes, in hot water extreme pools at very high temperatures. This shows you the temperature range where life occurs from minus 50 up to well above boiling point. Okay, so things are possible. These may be bacteria or fungi, or in this region where we are, this is the ocean, fish, etc. And then making one's way up to insects and all sorts of more complex things. And then lots of bacteria. They're a very dominant part of life on the Earth. And things would have begun there, we think. Okay. So that's good. So when we think of looking elsewhere in the galaxy, we want to choose the right place to look. You don't want to look too near the sun, right? Mercury might not be a good place to look for life. It's too baking hot there. But further out, and you could go maybe a lot further out, life might be not impossible. So here is another way of expressing this. We believe that what you need for life are basically three things. You need some liquid environment, so these complex organic material is mobile, can come together. You need energy to trigger the breaking up of compounds, creating new ones. That's typically sunlight. And you need this fundamental organic material, which we think can come into existence inevitably in some, maybe ultraviolet 3, deep ponds, Darwin, shallow pools. Things can gradually evolve over long times, over billions of years. So that's a current belief. And so when you look at all the possible planets that we've been discovering in the past 10 years, with space telescopes mostly, a few ground-based ones, you can look at this contribution. So this is the sort of a habitability index, okay, which means the amount of liquid water, basically, and similar things. And this is a sunlight index. You don't want to be in total darkness or have too much sunlight, you'd burn. And so, the Earth is in a very good place, very habitable, and just the right amount of sunlight. Mars isn't quite as well favored. I'll show you why in a second. And Venus would be too hot, etc. But out of all these planets, you can see there are others not too far away that should be very good candidates. We haven't got big enough telescopes yet to look at them, but we think, and this is just a sample of the nearby, within a few 100 light years or so of the planets we've been finding in the recent past. Okay, so. The solar system then, a wonderful collection that we have studied best, of course. And Saturn, you'll recognize, Jupiter, these are not very good places for life. They're methane-rich atmospheres. There's a tiny rocky core under immense pressure in the center, no surface on which you can imagine life ever evolving. But, the Earth is a good place that's not too close to the sun, not too far from the sun. So, it's at roughly the right temperature for life to develop. And then we have the outer planets, Uranus and Neptune, eventually Pluto. They're probably too cold for life to be significant there as well. Nevertheless, we have to look and study these. And so places that I'm going to tell you about a little bit in a moment are really interesting. We haven't found any evidence of life yet, but will be some of the satellites, for example. These are the satellites of Jupiter. This one, Titan, is the largest moon in the solar system, goes around Saturn, and this is a remarkably icy moon that goes around Saturn, and I'll tell you a little bit about conditions on those things to give you some feeling for where we might start looking or thinking about where life might or might not be. And so we've made lots of pretty pictures, discoveries of all the moons in the solar system. Titan is the biggest, and there are a lot of others that in the past 20 years or so our spacecraft have been imaging. Right, okay, so let's then consider where you'd want to look near us. The solar system is accessible. In principle, we can even go there one day. We have been already to one or two places, and we can send robotic probes to ones further away. So Venus, as I said, is a bad place to go because it's got a very dense atmosphere, incredible greenhouse effect. That means all the sunlight is, as in a greenhouse, it's absorbed on the surface, it's reflected, and the clouds basically trap the light, trap the heat, it's incredibly hot. There's clouds of sulfuric acid, it rains sulfuric acid. You can't imagine that would be a good place to search for life. The moon we haven't found anything very interesting there. Mars is a good place, I'll show you, because Mars, we see evidence that there once was a dense atmosphere like that on the Earth. There once was rain, there once were lake beds. We see the dried out lake beds, we see the dried out rivers, I'll show you in a second. Enceladus is another interesting case. It's an icy satellite, an icy moon, but lots of water seems to be there, which is one of the ingredients we need also. And Titan, I'll show you that because that has an interesting property too, that is reminiscent of life, but it almost certainly has nothing to do with life. Okay, so the moon. Okay, so we've been there. This is so far all that the basic Western presence, I would say, on the moon from the American landings on the moon. The only other presence at the moment is Chinese. The Chinese do have a small land rover on the moon with a telescope, which is exploring the moon as we speak. And there is a strong interest now in the space agencies, both American and European, to go back to the moon and do something more ambitious there with a human presence. So I'm not going to talk about that today, but that is the moon. But we don't expect to find life on the moon. There's no atmosphere there. There never was an atmosphere. It gets incredibly hot during the day, incredibly cold at night. Nothing could really survive those extreme climates as we think of life, but one could imagine setting up a base there, but that's a whole other story. But Mars is a different story altogether. So here is the Mars land rover, Curiosity, launched by NASA, landed on the moon in 2013, and is still roving around the moon, moves very slowly, a few kilometers per hour, but it's able to take wonderful photos. And I'm going to show you some of the images of the Martian landscape. And you can see, one is seeing hills, rocky features, impressive terrain, rocky terrain on Mars. And all of this tells you, when you see pictures like this, the geologists get very excited because they can tell that once there must have been erosion by water, which has led to the formations of these rocks, just as you see in riverbeds and dried out riverbeds on the Earth. So there once was a lot more water than we see now, and a lot more atmosphere to contain all that water, stop it from evaporating. And here is an image from the Earth showing you, if you go to a desolate desert on the Earth, this one's called the Valley of the Lune in the Atacama Desert in Chile, you can see all these similar rocky features, which are due to erosion by the atmosphere, erosion by flash flooding, various things like this. And we're seeing features like that on the landscape of Mars, which presumably formed a very long time ago. These are sand dunes on Mars. Again, beautiful pictures, reminiscent of what we see on the Earth. These are two more examples. This is a large crater, and you can tell from the fissures on the side that this must almost have been certainly formed by a process of water freezing and so forth a long time ago. And this is another example of the Martian landscape. All these formations demonstrate that there once was incredible erosion, once was a significant atmosphere. Once upon a time, billions of years ago, Mars might have been a bit like the Earth. Okay, so what we want to do next, clearly, is, we have the land rover wandering around the surface of Mars, but the future of Martian exploration will be to go to Mars and dig deep, and look for traces deep down of possible organic materials. And so that is really the focus of Martian exploration in the next decade or two. And we have these wonderful rocky landscapes to explore on Mars. Okay, so this is just incredible. Looks, again, you can see much like the Earth does, but of course these are just much, much older. On the Earth, our typical ranges like this are hundreds of millions of years old. On Mars, these certainly formed billions of years ago. And water's been found on Mars. Another amazing photograph. We see evidence of water. This is ice near a valley on the moon. So abundant ice, still frozen out, and no doubt evaporating slowly, but apparently this again tells you Mars could well have had a glorious past, and we want to look for evidence of that by digging deep, evidence of life. But that's not going to help us with the basic question of finding life, we think, very easily. So before I go further away, let me show you another amazing object in the solar system. So this is an icy moon, which covered in ice, and you can see it's been bombarded by many meteorites. It's got no atmosphere, and the meteorites leave these pockmarks throughout the surface of Enceladus, which is a moon, a small moon going around Saturn. And so this is, you can now see the landscape, a close-up, taken by the recent Cassini probe before it crashed into Saturn. And so you can see there's amazing features in the ice, history of bombardment, but there's a big sheet of ice over the entire planet. Is a close-up. Amazing terrain someday for our astronauts to explore. That will be a long time in the future. But the most amazing discovery of all is there are volcanoes on Enceladus, and the volcanoes of water. So it's erupting and giving you these amazing geysers of water going thousands of miles above the surface, up to thousands of miles above the surface, hundreds of miles in this case. And so it's clearly, despite it being so far out, away from the sun, where it is very cold, it still has retained enough internal heat to give you these, and instability, seismologically speaking, to give you these features. And again, this suggests that it's not impossible to imagine that there could be life, given you have water there, some sort of life forms under the ice surface, in principle. And so that's another target. Enceladus and its sister satellite called Europa, those will be targets for future exploration for space experiments. Okay, and then finally, finishing my brief tour of the solar system is Titan, the largest moon in the solar system, orbits around Saturn. And so at first this seems just a fairly nondescript sort of object, but what is unique about Titan is this. It's got fog, if you like, haze. So this is, so above the surface, which is here, you can see this faint glow. This is basically haze, the same haze you see in the sky, on a polluted day in a big city typically. If you look at the horizon near London, you can see brown haze sometimes. But that haze around London is probably due in part to biological signatures. When even even far from the cities in the wilderness, you can see natural haze arising from vegetation, right? So that would be a sign that we would look for in when we study distant planets. Unfortunately, this particular haze we know is methane induced. Methane compounds being disintegrated by sunlight, giving you this haze on the surface of Titan. But it's the example of what astronomers want to look for, a more organic type of haze. That's why they want to study exoplanets in more detail. Okay, and Titan also has these amazing lakes of methane. So look at this amazing picture. These are methane-full lakes, again, thousands of miles from here to here. On the surface of Titan. So it again will be a wonderful planet to explore, but probably nothing to do with life. But it just shows you the richness we have, and the many environments that are interesting will be explored in the future. Okay, so life then. This is the main goal of my talk. We want to find, we call them exoplanets. These are planets around other stars, basically, and ideally Earth-like planets, that is at the right distance from their host star, not too close, not too far away, with atmospheres massive enough to hold on to their atmospheres, not too massive, so they may be too icy or whatever, but just about right to foster life. We only have one example of life in the universe, that's us. Okay, so we know that life began somehow on a planet like the Earth. And so that is, simple-minded as it may seem, that's our guide when we study the cosmos, to look for twins of the Earth, basically. Okay. And so there are lots of exoplanets out there. There are more exoplanets than stars in the universe, that's certain, okay? But most of them will not be too good for life, not be too hospitable for life. So we're going to have to settle in the next few decades for studying the nearest ones, because they're the only ones we can study enough detail to get some feeling for this. Okay, so we're just going to look at the nearest stars and get to work. So this is a very tough business, because if you imagine a planet around a nearby star, the star is incredibly bright. Imagine going into a room, coming in from the dark, as it were, and then someone turns very bright lights on. You're just dazzled, right? You simply can't see any dim things in that room anymore. It's the same with an exoplanet near its host star, the Earth around the sun seen from far away. The star is shining so brightly that you can't possibly see the planet, even though in principle it should be visible, okay, as a little blob or something, or a faint blue dot, as Carl Sagan famously once called what the Earth would look like viewed from far away. You've got to remove that starlight in your experiment, in your camera, by you're looking for 1 part in 10 billion. You've got to, remove all the rest of that light, and you have to do this artificially. And so there's a very clever way that we're going to do this with what is called a star shade. Okay, so the idea is that you have a future space telescope. This is supposed to be launched in the mid-2020s, 2025 or thereabouts. It's got a name, WFIRST. And another satellite has launched a giant umbrella, right, which unfurls, okay? This is many thousands of miles away, okay? And this is the size of a tennis court, okay? And the idea is you use this as an occulting screen. So when you look at a nearby star, you occult the star and look for the planet just you've suddenly reduced the effect of blinding your telescope by the bright star using the principle of just occultations. So that we're actually, these things are being built, and maybe in a decade's time, we'll be able perhaps to directly image planets. The idea is we want actually to image a nearby planet. Okay, just as we see the ones in our solar system, we want to image them far away, and we're going to look at stars that are many light years away, because that's where we have a larger selection of planets. Given the small sample that we have in our solar system, only the Earth and Mars are possible hosts of life, okay, and Mars we haven't seen yet for that. But if you have enough samples of stars, enough planets, you're going to find enough Earth-like twins where you can, start looking, and that's the aim of this experiment. Okay, so let me tell you how we're going to decide there is organic life on this distant exoplanet. And so it's an amazing story, really, because what you're looking at is the moon, the crescent moon. And if you ever looked at the crescent moon in a dark area, you know the rest of the moon, the dark part, is glowing very, very slightly. You see a dim glow. And what you're seeing in that dim glow is earth shine. So you're seeing reflected light from the Earth. And so then what you can imagine doing is using this as a diagnostic of an Earth-like atmosphere. You would then go to your distant planet, and then you take a spectrum of it, you divide the light up into individual components of different lines, and this is what you hope to do. So when you take the spectrum of Earthshine, this is Earthshine, you see all these components which you diagnose as water. But the most amazing thing of all is you see what is called the red edge, a dip over here, okay, which is produced by vegetation, by basically the effects of photosynthesis give you this unique feature in the spectrum, okay, because the plants re-radiate the sunlight in the infrared, basically. And so you get a sudden dip on a certain wavelength and an increase in the other. So the red edge is what we're going to look for. And Earthshine shows you what the Earth should look like. And so the idea is now when we find our nearby star, we eclipse the star away with our coronagraph. We take a spectrum of the dot that we see next to the star, the planet, and we look for the effect of vegetation. So that's the idea. So we haven't got there yet. It involves building bigger and better devices, but this is a definite program that will be done in 10 or 15 years' time. Okay. So here's another possible signature of intelligent life, and here we should put the words intelligent in quotation marks, okay? So if you take a similar spectrum of the sky above Los Angeles or London, you'll find that in the constituents of the atmosphere, which in principle you can see in a distant exoplanet too, those constituents include industrial pollutants, ones which don't occur naturally but are made by our factories, okay? Smog, if you like, industrial smog. And so if you found industrial smog in a distant exoplanet, that would be a sign of they had advanced life, okay, because they're happily polluting their place. The problem is that industrial pollution may not, the phase at which civilization does that may not last very long. And I'm speaking now cosmically speaking. Clearly we're going to have it for another 100 years or 1,000, but I imagine in a few hundred years' time, think about the Earth, we surely will have understood enough about industrial pollution to clean our act up, okay? If we even survive that long, thanks to other possible calamities, then this might be a transient signal, okay? Fine, so another transient signal of intelligent life in the universe, again in quotation marks, would be the signs of nuclear war. So when you explode nuclear bombs in the atmosphere, you produce highly toxic radioactive signals. And some of these isotopes are very long-lived, okay? Many thousands of years. Cesium, for example, 30,000 years is its half-life. So you can expect then that, again, if you can diagnose the atmosphere of a distant exoplanet, you might look for very unusual man-made indicators of nuclear explosions, for example. That's another prediction. Again, hopefully that also would be a transient phase of a civilization. But of course, it might be a fatal phase, which would mean that would limit the number of objects you could ever hope to see, right? If it only lasted, if your civilization was capable of destroying itself in a few thousand years, then that you'll need a huge sample of exoplanets to find this before, if it did occur elsewhere, and that won't be easy either. So, okay, and so here's yet another approach, which is a little more proactive. This is Jill Tarter, who's head of a project called SETI, and SETI means Seeking Extraterrestrial Intelligence. Okay, and the idea is they go to some of the world's largest radio telescopes. This is one in Puerto Rico. It's a kilometer across. It's in a huge natural crater, and it receives radio waves, big radio antenna. Here's the focus, and the radio waves get reflected back here, and then they get analyzed by computers. And so this radio telescope studies distant galaxies, distant stars. But at the same time, the SETI organization piggybacks on board, and they attach their own device which looks for signals of electromagnetic communication. So for example, if you had some distant planet which had advanced life, and let's suppose it's 50 light years away, right? Then 50 years ago, if it were like the Earth, it would have been broadcasting I Love Lucy, and then on the Earth, we would just be catching it right now. So they are basically listening for TV shows or whatever, or maybe more advanced types of communication from distant planets. Of course, they've found nothing yet, but the technology is interesting. So they basically gather all of this data and look for weird signals which might be coherent in some way, and that could be deciphered, even though, of course, the native language wouldn't be English or anything, whatever, but you would look for some pattern that would be non-random. Okay, they've found nothing yet, but it's an activity that goes on in many telescopes like this around the world, radio telescopes, to look for these signals. Okay, so here's one more example. So I should say that, again, that might be a transient thing too, because my view is that if you imagine, right now, we're happily broadcasting our TV signals into space, right? And so if you think about it, eventually, if we've been doing this for 40 years or 50 years, eventually they'll have gotten 40 or 50 light years away. But I imagine one day we'll think of much more energy efficient ways using fibers, for example, optical fibers, to obtain our TV, our communication, and then you won't wastefully send them out in space. So it may be, again, this business of looking for radio signals from far away is also a transient thing. But there's one way of looking for distant life that is very hard to hide. And the idea is that any distant advanced civilization has basically to use energy, and a lot of energy, okay? As you know, we seem to need more and more to power our computers, to drive our cars, etc., etc. And energy always leaves behind waste heat. There's no such thing as 100% efficient use of energy. There's always waste heat, and often quite a lot of waste heat. And so the waste heat is something you can look for in the infrared, okay? That's where it comes out. And it was, I think, Dyson that first suggested, well, what is the ultimate energy source, he argued, for a planet around a star? Well, if you think you wanted solar energy, we know is the future, right? Most of us would agree on that. And we're busily going in that direction, some countries faster than others on the Earth. But most of the solar energy is wasted, right? It just goes out randomly into space, okay? So that's, so if you really wanted energy, you could think of a much more efficient way. If you want to start, for example, launching probes to nearby stars, whatever, you need huge amounts of energy, okay, at advanced civilization. So the way Dyson conjectured was that imagine trapping all the energy from the sun in what's been called a Dyson sphere, named after him, and this energy would be trapped, could be used, but eventually you'd get infrared light. Heat energy would still go into space. You'd convert all that energy, all the optical light, the ultraviolet light from the star, you could use that to run your transistors, your computers, your transport, whatever you want to do, but heat would escape. So he said, well, maybe a truly advanced civilization, now we're thinking one's hundreds of thousands of years, even a million years' time, and the time scales are mind-boggling, right? Look how much progress we've made on the Earth in a couple of thousand years, right? 100 years since the Industrial Revolution. But that is nothing compared to cosmic timescales. There are planets out there, most of the planets, in fact, have 1 billion years advance on the Earth. Just imagine that. You can't begin to imagine what you can do in 1 billion years, if you don't destroy yourselves, obviously. That's a whole other issue. But so anyway, so Dyson spheres are, and so what he said was that if extraterrestrial intelligent beings exist and have reached a high level of technical development, one byproduct of their energy metabolism is likely to be the large-scale conversion of starlight into far-infrared radiation. So that was the idea, beautiful idea. And we've been looking, and it's interesting. So far, we've found nothing, but there is one candidate. And so let me tell you about that one. So it's a weird star found by this American astronomer, detected for the first time. And it's a star that has these very odd variations, but enormous variations in energy every few months, okay? And no other star looks like this, okay? And so it's been conjectured, not necessarily by her, but people who interpret her data, that this could be due to asteroids or lumps falling into some star, and possibly giving you these natural variations, which are enormous and require energy amounts like that. So that's probably the most likely possibility, but I should say that this energy is seen in the infrared. And so here is another conjecture, which is that this star, in fact, has some advanced type of, this is not a Dyson sphere, but these are bands around it designed to trap starlight much more than any one planet would. And that what one is seeing is the erratic starlight as it crosses these bands, okay? And so that's a totally, I would say, crazy conjecture. It's sort of signal you can imagine looking for from some super advanced civilization. Obviously, you want to find more examples of this and do follow-ups of the stars, look at planets, whatever, but that's the sort of thing you could imagine happening someday. Okay, so let me tell you now what maybe, what is really happening, okay? And this maybe is one of the most fascinating stories in this whole question of let's look at a nearby planet, okay, and exoplanet, and let's look for signs of life. So again, this has a very low probability of actually finding any signs of life, but you have to start by looking. And so here's an incredibly good way to get a close-up view of nearby planets, okay? And the only way you can do that is by going there, okay? At the nearest star that has planets is 4 light years away, okay? It's in the system Alpha and Proxima Centauri. And so what this US-Russian millionaire is proposing and is funding is to send miniature cameras there, but in tiny spacecraft propelled at a huge speed, roughly as high as 1/10 the speed of light. Now, if you can go 4 light years at 1/10 the speed of light, that means you get there in 40 years. And so they could send their signals back, and 4 years later, we would have lots of pictures. That's his idea. So let me show you how this incredible story works. You have a bank of lasers, okay? Huge bank of lasers, gigawatts of lasers on somewhere. Hopefully not on the Earth, but that's another story. And here is a light sail, a tiny mylar sheet. It's just like the principle of sailing, basically. And there's a tiny camera at the focus of it. The camera is a very clever electronic chip of silicon, and it just weighs grams, okay? And the idea is the laser beams, light's got pressure, right? It can push things. So with enough power in the laser beams, you can push this sail, and it will basically pick up enormous speed. It can go up to 1/10 the speed of light. If you keep on pushing it, then you turn off the laser beams, it just keeps on going, okay? So, and then they will direct not just one of these, but maybe thousands of them will be sent off to go to Proxima Centauri. And in 40 years' time, they will get there, etc. So funding is still, this project is being designed, and it maybe is our best way to get close-up images of exoplanets, the same quality as the ones we have of Mars and the other planets I showed you, but now we'd be discussing them, seeing them around the nearest star with a planetary system much like the one around our sun. So that's sort of somewhat of a mind-boggling story too. Okay, so let's come back to intelligent life, right? Maybe when you do this project Starshot, it's being called Breakthrough Starshot, you could find evidence of vegetation. That would be amazing, right? You could see the forests and the oceans. That would be the hope, okay? And so you'd have some chance of that. But intelligent life is a different question, because that's going to almost certainly be quite rare. So how do we estimate the frequency of finding intelligent life around us? So a major idea in this field was generated by a radio astronomer called Frank Drake. And he said, let's try to estimate the probability of finding life. And so there are many, many uncertain factors. One might be the number of exoplanets, right? Now we're measuring them, so we have a rough idea how many there are. Another might be whether they have atmospheres, oxygen-rich atmospheres. Another might be, do they have oceans? Do they have the right conditions for life? Another might be, are they at the right distance from their host star? Another might be, the host star mustn't be too hot a star or too cold a star. So just must be a bit like the sun, right? The same type as the sun, more or less, okay. And so on. But it turns out that you can estimate all of these things, but the biggest uncertainty in this equation, it's a sad uncertainty really, it's with the duration of time that intelligent life will exist, okay? So if intelligent life blows itself up or destroys itself, whatever reason, maybe an asteroid hit that planet or something, all sorts of things could happen, right? And if that's too short a time span, then life is incredibly rare. On the other hand, if you're clever enough, you can imagine even thinking of ways, we're exploring them already on the Earth, to help deviate asteroids that might come too close to the Earth and potentially repeat the dinosaur destruction 60 million years ago. That there are clever ways that one, if you just take them far enough away, that you can perhaps, do something about that, or maybe not. But again, that's what we're doing today, but you can imagine that in 1,000 years, we'll have perfected that technology, so one could presumably, not worry about that particular existential risk. But there are many others that are more difficult to protect oneself from, such as runaway nuclear war, or concoction by some teenager of some virus that which one can do in principle nowadays that would poison all the water on the Earth. Who knows what. So there are many risks that we have enough skills in molecular biology, for example, that example, and in technology to imagine developing that we don't really know how to protect ourselves against. These are simply risks that make it totally uncertain as to what calculation you can do to estimate how many possible alien type civilizations might be out there that would have survived long enough to be truly advanced compared to us. Okay, so what you have to remember then is life is highly fragile. So this is my asteroid picture. This asteroid, beautiful impact crater, didn't have a huge impact on life, but there are ones in known history that did have significant impacts. creating dust that lasted a very long time, etc., which was not good for life. And the dinosaur impact, the major asteroid impact, had a catastrophic effect in cutting the number of species at that time by some huge factor. So life is fragile. Life is also very tenacious. So I showed you examples of life at high temperature. Here's another example of, this is one of the ponds, hot ponds in the Yellowstone National Park, hundreds of degrees, right, temperature, and yet life, this coloration in the water is due to organic life in such extreme conditions. So life can resist many things, and maybe you could say that you could even basically survive nuclear catastrophes or other catastrophes. So, well, climate change is another big issue. You know, if we suddenly get into extreme climate change, that may be a huge setback in advanced civilization. It may take us back to the Stone Age, for example, right? Not a pleasant place to be, maybe, but life can recover, okay? What's amazing about history is it tells us that maybe over thousands of years, 50,000 years if you like, since really primitive times, life was able to recover. And what that means is that if your destruction time is 5,000 years and your rejuvenation time is 50,000 years, you simply have to search 10 times as hard. You simply need 10 times more targets. It just reduces your chances of finding life by 10, which is not much if you have hundreds of exoplanets, thousands of exoplanets. It just means you have to do a little better. Okay, so that seems to me the optimistic view about looking for life elsewhere. Okay, well, why are we so optimistic that there should be life out there? So this is something that was stated, a long time ago, Lucretius. It's just highly unlikely that this Earth and sky is the only one to have been created. Nothing in the universe is the only one of its kind. So that's, very fundamental philosophical reasoning. And I think there's a lot to be said for imagining that there should be other stuff out there. But as to quantitatively, how hard you have to look, that's a totally different question. The number of exoplanets that the biggest telescopes we're designing now will be able to detect that are reasonably comparable to the Earth is going to be between 10 and 100. That's the plan for the next 2 decades. We just can't imagine building bigger telescopes, building bigger star shades. So we'll have maybe 10 to 100 exoplanets, which are, quote, not Earth-like, more or less. And with those 100 exoplanets, we'll be able to, again, with advanced technology, look at their atmospheres, look for signs of vegetation, and that's the program for the next couple of decades, to look for traces of what might be out there. But if life is fragile, well, maybe the vegetation can regenerate, whatever, but if it's intelligent life you want, then it's certain that is simply not a large enough sample. And so that, I think, is a big question for the more distant future, how we look for these things. If by chance a project like Project SETI can work, then yes, fine, we'll hear some form of noise that will demonstrate there is something out there to focus on, maybe have a conversation with, even though it takes us 100 years for a message to pass or more, right? But in principle, one can take the long-term view and imagine that. But that, again, seems to be highly unlikely because that already presupposes that, such things might be there within 100 light years of us, and that's such a small distance, astronomically speaking. There are, relatively speaking, only thousands of, maybe hundreds of thousands of planets in that volume, and that may not be enough. You have to really search for the few possible interesting places in our entire Milky Way galaxy to have high confidence that you might find something, and that seems to be a really impossible task at this moment. So the question is likely to be very, very hard to answer. Life, yes. Organic life, yes, that I think is a realistic search. The red edge I showed you, the sign of vegetation in the spectra of distant exoplanets, that is a real possibility, okay, that we might be able to detect that. And that would be an amazing breakthrough. But going beyond that is going to be just a question of luck, maybe. And so let me conclude by giving you the ultimate philosophy behind, the astronomers, the physicists who want to look for life. And so few will deny the profound importance, practical and philosophical, which the detection of interstellar communications would have. We therefore feel that a discriminating search for signals deserves a considerable effort. The probability of success is difficult to estimate, okay? But if we never search, the chance of success is zero, okay? So that is the ultimate word, I think. We have to keep on looking. Maybe there'll be surprises. There surely will be surprises that we cannot even begin to conjecture about. But I think our optimistic hope in astronomy is that by building some of these futuristic, expensive telescopes, we hopefully will find evidence for atmospheres and vegetation on distant exoplanets. And that will be a major, major step forward. And that is going to take us the next 2 decades of exoplanet exploration in astronomy. So thank you.